In 1858, engineers completed a masonry tower on a granite outcrop 16 miles from the nearest landfall, designed to withstand the most severe marine conditions in British waters. The structure incorporated established principles of lighthouse construction: massive interlocking stone blocks, dovetail joints, and metal anchoring systems that had proven successful in less exposed locations. Calculations assumed wave forces could be adequately resisted through sheer mass and traditional joinery techniques. The lighthouse operated successfully under normal conditions, providing reliable navigation guidance exactly as intended. Within decades, however, inspection revealed stress fractures in the exterior granite blocks and evidence of structural movement during severe storms. The original engineering assumptions had not accounted for the unique dynamics of breaking wave impact on an isolated vertical structure in deep water. The design philosophy that prioritized proven construction methods over empirical testing of extreme loading conditions had embedded a fundamental limitation. Traditional engineering approaches, successful in coastal applications, could not be validated against the actual forces generated by the most violent Atlantic storms. The structure functioned precisely as designed under anticipated conditions, yet failed to perform adequately under the environmental extremes it was specifically built to endure. The isolation that made the lighthouse navigationally essential also prevented engineers from directly observing and measuring the forces their design would face. How does engineering confidence in proven methods obscure the need for empirical validation of unprecedented applications? Bishop Rock Lighthouse represented the culmination of a century of lighthouse engineering evolution, yet it embodied assumptions that would prove fundamentally inadequate for its intended environment. The structure rose from a 47-meter-long, 16-meter-broad granite outcrop that dropped into 37-meter deep water on all sides. This location, approximately 8 miles southwest of the Scilly Isles, placed the lighthouse in one of the most exposed marine environments around the British coastline. The site's navigational importance was undeniable. Bishop Rock marked the final hazard for vessels entering or leaving the English Channel from Atlantic approaches. Yet this same exposure that made the lighthouse essential created environmental conditions that exceeded the empirical foundation of 19th-century lighthouse engineering. The design philosophy underlying Bishop Rock derived directly from John Smeaton's revolutionary third Eddystone lighthouse completed in 1759. Smeaton had introduced the concave elliptic frustum profile, reasoning that this shape would deflect wave energy upward rather than absorbing horizontal impact forces. His approach represented a fundamental shift from earlier lighthouse designs, which had relied primarily on massive vertical walls to resist marine forces through static resistance. Smeaton's innovation lay in recognizing that wave deflection could be more effective than direct resistance, particularly for structures exposed to severe Atlantic conditions. However, Smeaton's empirical foundation was limited to the specific conditions at Eddystone Rocks, located approximately 14 miles south of Plymouth. While Eddystone represented significant exposure to Atlantic weather systems, the site differed fundamentally from Bishop Rock in critical aspects. Eddystone sat in approximately 18 meters of water at high tide, roughly half the depth surrounding Bishop Rock. This difference in water depth created entirely different wave dynamics during severe storms. At Eddystone, waves approaching the lighthouse had already begun shoaling and energy dissipation before impact. At Bishop Rock, deep water extended almost to the base of the structure, allowing storm waves to maintain their full energy until the moment of impact with the granite foundation. The engineering calculations underlying Bishop Rock's design relied on wave force estimations, derived from static pressure principles. These calculations, developed from observations of wave action against coastal structures, assumed that maximum wave force could be calculated as a function of wave height and water density. The standard approach multiplied wave height by water density and gravitational acceleration to estimate maximum pressure. For a 10-meter wave, this calculation yielded approximately 100 kilonewtons per square meter of applied pressure. Engineers then applied safety factors, typically ranging from 2 to 4, to account for uncertainty and dynamic effects. This methodology contained a fundamental flaw. It treated wave impact as a static pressure application rather than a dynamic momentum transfer. Breaking waves in deep water carry enormous kinetic energy that converts instantaneously to impact force upon collision with a vertical structure. The momentum of thousands of tons of moving water creates forces that can exceed static pressure calculations by orders of magnitude. Moreover, the duration and repetitive nature of wave impact during extended storms introduces fatigue considerations that static calculations cannot address. The masonry construction methodology employed at Bishop Rock followed established practices that had proven successful in terrestrial applications and less exposed marine environments. The foundation courses were cut directly into the granite outcrop, with each stone secured by fox-wedged Muntz metal bolts sunk 0.3 meters into the rock. Muntz metal, a brass alloy of 60% copper and 40% zinc with trace iron content, provided excellent corrosion resistance in marine environments. The fox wedging technique involved driving a shaft through each block onto a wedge set in the end face of a recess that broadened with depth. This created a mechanical lock that prevented vertical displacement under normal conditions. Above the foundation level, the Lighthouse employed dovetailed granite blocks arranged in 70 courses rising to a height of approximately 30.5 meters. Each course consisted of pre-shaped granite blocks, typically weighing 2 to 4 tons, quarried in Cornwall and transported by ship to the construction site. The dovetailing system created both vertical and horizontal interlocking between adjacent blocks. Face stones in the external ring incorporated raised dovetail bands on their upper surfaces and ends, with corresponding dovetailed recesses cut into adjoining stones. The dimensional tolerances allowed the raised bands to enter the recesses freely during positioning, while providing mechanical resistance to displacement once the blocks settled into their final positions. The structural logic underlying this construction method assumed that the combination of massive stone weight, mechanical interlocking, and metal anchoring would create a monolithic structure capable of resisting any conceivable marine force. Each course was secured to the course below by galvanized puddled steel bolts, 50 millimeters in diameter, sunk 0.23 meters into the lower course. Between courses 3 and 20, each external face stone received 2 such bolts. The engineers calculated that this anchoring system, combined with the gravitational loading of the masonry mass, would prevent any significant displacement under wave action. The materials selection reflected the highest standards of 19th-century engineering. The granite blocks were quarried from Cornwall deposits known for exceptional durability and compressive strength. Laboratory testing of sample blocks demonstrated compressive strengths exceeding 200 meganewtons per square meter, more than adequate for the calculated structural loads. The use of Medina Roman cement below high water spring tide levels and Portland cement above provided chemical bonding between blocks while allowing for slight differential movement. Experiments conducted during construction demonstrated that properly cemented joints could achieve strength equal to solid granite. However, these material properties and construction techniques had been validated primarily under static loading conditions or relatively modest dynamic loads. The testing protocols of the period could not replicate the extreme dynamic forces generated by breaking waves in deep water during severe Atlantic storms. Laboratory compression tests, while useful for establishing baseline material properties, could not simulate the complex stress patterns created by rapidly applied impact forces followed by immediate pressure release and subsequent impact repetition. The design process reflected the institutional confidence of Victorian engineering in analytical methods and proven construction techniques. The project engineers working under the authority of Trinity House approached the Bishop Rock challenge as a scaling exercise, rather than a fundamentally new engineering problem. The successful performance of earlier lighthouses, including Smeaton's Eddystone and similar structures around the British coastline, provided empirical support for the basic design approach. The engineering profession had developed sophisticated analytical tools for calculating structural loads, material requirements, and safety factors. These tools had proven reliable across a wide range of applications, from railway bridges to industrial buildings to marine structures. Yet this analytical confidence obscured a critical limitation. The empirical foundation for extreme marine loading was exceptionally narrow. Unlike terrestrial structures, where loading conditions could be observed and measured directly, Offshore lighthouse design required extrapolation from limited coastal observations to unprecedented exposure conditions. The engineering profession possessed extensive experience with static loads, moderate dynamic loads, and periodic loading cycles. It lacked empirical data for the extreme dynamic impact forces characteristic of breaking waves in deep water. The construction timeline for Bishop Rock revealed another constraint that affected design validation. Initial construction began in 1851, following detailed site surveys and design development. However, the extreme exposure of the site limited construction work to brief periods of favorable weather. Construction crews could access the rock only during calm conditions, which occurred primarily during summer months and brief winter interludes between storm systems. This constraint meant that engineers and construction workers never directly observed the site under the extreme conditions their structure was designed to resist. The original lighthouse, completed in 1858 at a height of approximately 30.5 meters, incorporated all the established principles of lighthouse engineering. The structure featured Smeaton's concave elliptic frustum profile, massive granite construction, sophisticated joinery, and metal anchoring systems. The design calculations indicated adequate safety margins for anticipated wave forces. The construction quality met the highest standards of the period. The lighthouse began operation immediately upon completion, providing reliable navigation guidance for vessels transiting the western approaches. Within 2 decades, however, the structure exhibited clear evidence of structural distress. Inspection reports documented vibration during severe storms, with the lighthouse exhibiting measurable movement under extreme wave action. More critically, examination of the exterior masonry revealed stress fractures in multiple granite blocks, particularly in the middle sections of the tower, where calculated stresses should have been well within safe limits. Some granite pieces, weighing up to 25 kilograms, had split completely away from the exterior face during violent storms. These observations forced a fundamental reconsideration of the design assumptions underlying the original structure. The evidence indicated that actual wave forces significantly exceeded the calculations upon which the design was based. The dynamic nature of breaking wave impact created stress patterns and magnitudes that static analysis had not predicted. The repeated application of these extreme forces during extended storms introduced fatigue effects that gradually degraded the structural integrity of the masonry system. The engineering response to these discoveries would ultimately validate the inadequacy of the original design approach while demonstrating the limitations of attempting to retrofit structures designed under fundamentally flawed assumptions. The experience at Bishop Rock illustrated how institutional confidence in proven engineering methods could obscure the need for empirical validation when those methods were applied beyond their validated range of conditions. The isolation that made Bishop Rock navigationally essential created construction constraints that prevented engineers from directly observing the environmental forces their structure would encounter during operation. The lighthouse's location, 16 miles from the nearest substantial landfall, required all personnel and materials to be transported by ship during brief weather windows. This logistical reality fundamentally shaped both the construction process and the engineering validation opportunities available during the project's development phase. Construction at Bishop Rock could proceed only during periods of relatively calm weather, when seas allowed safe boat approach to the granite outcrop. Historical weather records from the period indicate that suitable working conditions occurred primarily during late spring and summer months, with occasional brief windows during winter periods between major storm systems. Trinity House construction logs document that during the 7-year construction period from 1851 to 1858, actual working time on the rock totaled fewer than 1,200 hours. This represented less than 20% of normal construction productivity, creating enormous economic pressure to maximize efficiency during accessible periods. The construction methodology reflected these constraints through emphasis on prefabrication and rapid assembly techniques. Each granite block was quarried, shaped, and finished at mainland facilities before transportation to the site. The dovetailing patterns, bolt holes, and surface preparations were completed on shore, allowing construction crews to focus exclusively on positioning and securing blocks during their limited time on the rock. This approach minimized weather exposure but eliminated opportunities for real-time design modifications based on environmental observations. The professional training and experience base of the construction workforce reflected the terrestrial lighthouse construction tradition that had developed over the previous century. Master masons, stone cutters, and construction supervisors brought extensive experience with coastal lighthouse projects, including work at Eddystone, Skerries, and other exposed locations around the British coastline. Their expertise encompassed the traditional techniques of granite cutting, dovetailing, metal anchoring, and masonry construction that constituted the technical foundation of lighthouse engineering. However, this experience base contained a critical limitation. None of the construction professionals had worked under the extreme exposure conditions that Bishop Rock would experience during operation. The construction weather windows, by necessity, excluded the severe storm conditions that represented the lighthouse's primary operational challenge. The workforce could observe and adapt to normal marine conditions: moderate waves, tidal variations, salt spray, and typical Atlantic weather patterns. They could not observe the breaking wave dynamics, extreme wind loading, or sustained storm conditions that would ultimately test the structure's fundamental design assumptions. The project management structure reflected Trinity House's institutional approach to lighthouse construction, emphasizing proven methodologies and systematic quality control. The organization had developed standardized procedures for lighthouse construction based on decades of successful projects around the British coastline. These procedures specified materials selection, construction sequencing, quality inspection protocols, and safety measures that had proven effective across a wide range of coastal and offshore applications. The site supervision responsibilities fell to experienced Trinity House engineers who rotated assignments between multiple active lighthouse projects. This rotation system ensured consistent application of organizational standards while distributing specialized expertise across the lighthouse construction program. However, the rotation approach also meant that no single engineer maintained continuous observation of Bishop Rock's environmental conditions throughout the construction period. Site supervisors could observe conditions during their assigned periods, but could not develop the comprehensive environmental understanding that might have revealed design limitations. Communication between the construction site and the Trinity House engineering headquarters in London operated through written reports and periodic meetings during crew rotation periods. The communication protocols emphasized progress reporting, materials requirements, quality control findings, and safety incidents. The standard reporting format did not include systematic environmental monitoring or analysis of observed wave conditions relative to design assumptions. Construction reports focused on technical execution rather than empirical validation of engineering calculations. The economic incentives surrounding the Bishop Rock project strongly favored construction completion over extended empirical observation. Trinity House operated under parliamentary oversight and public scrutiny regarding both lighthouse effectiveness and construction costs. The organization faced pressure to complete navigation improvements efficiently while maintaining high safety and quality standards. The extended construction timeline already represented a significant financial burden, creating organizational resistance to additional delays that might be required for comprehensive environmental monitoring. The materials supply chain for Bishop Rock required coordination between multiple specialized suppliers across southwest England. Granite blocks were quarried in Cornwall, cut and shaped at specialized masonry facilities, and transported by coastal shipping to staging areas near the construction site. Metal components including bolts, anchors, and structural ironwork were fabricated at specialist foundries and machine shops. Cement and other binding materials were produced at established facilities and shipped according to construction schedules. This complex supply network operated efficiently, but created additional pressure for rapid assembly once materials reached the construction site. Quality control procedures during construction emphasized dimensional accuracy, material integrity, and adherence to specified construction techniques. Inspection protocols verified that granite blocks met dimensional tolerances, that dovetailing patterns aligned properly, and that metal anchoring systems were installed according to specifications. These procedures ensured consistent application of the design intent while maintaining the high craftsmanship standards characteristic of Victorian engineering projects. However, The quality control framework did not include testing of the completed structure under representative loading conditions. The inspection procedures could verify that construction met design specifications but could not validate whether those specifications were adequate for the intended operating environment. Load testing, where attempted, was limited to static loads that could be safely applied during construction. The quality control system possessed no mechanism for evaluating structural response to the dynamic impact forces that would characterize severe storm conditions. The knowledge transfer mechanisms within Trinity House reflected the organization's institutional learning approach, emphasizing documentation of proven techniques and systematic application of successful methodologies. Senior engineers maintain detailed records of construction techniques, materials performance, and structural solutions that had proven effective across multiple lighthouse projects. This institutional knowledge base provided the technical foundation for approaching new challenges like Bishop Rock. Yet this knowledge transfer system also perpetuated design assumptions that had not been tested under extreme conditions. The institutional learning mechanism was highly effective for preserving and refining proven techniques, but was not structured to identify situations where those techniques might be inadequate. The knowledge base emphasized what had worked successfully, rather than exploring the boundaries of applicability for established methods. The workforce development for lighthouse construction relied heavily on apprenticeship systems and learning through practical experience on successive projects. Master craftsmen trained apprentices through hands-on work, passing along both technical skills and practical judgment developed over years of construction experience. This training approach created deep expertise in traditional construction techniques while ensuring consistent quality across projects. However, the apprenticeship training model reinforced reliance on established methods rather than encouraging critical evaluation of design assumptions. Apprentices learned to execute proven techniques efficiently and reliably, but were not trained to question whether those techniques remained appropriate under unprecedented conditions. The training emphasis on craftsmanship and technique execution did not include systematic analysis of the relationship between construction methods and environmental loading conditions. The regulatory environment surrounding lighthouse construction in the 1850s emphasized safety of navigation rather than structural engineering standards. Parliament and maritime authorities focused on ensuring that lighthouses provided reliable navigation guidance under all weather conditions. The regulatory framework assumed that Trinity House possessed the technical expertise to design and construct adequate structures without specifying detailed engineering standards or requiring independent verification of structural adequacy. This regulatory approach created organizational autonomy that could be either beneficial or problematic depending on the adequacy of institutional technical capabilities. Trinity House could pursue innovative solutions and apply specialized expertise without external interference. However, the regulatory framework also provided no external check on design assumptions or construction methodologies that might be inadequate for unprecedented applications. The operational planning for Bishop Rock assumed that the completed lighthouse would require minimal maintenance beyond routine lamp maintenance and periodic inspection of structural components. The design philosophy emphasized durability and long-term structural integrity to minimize the expensive and logistically challenging maintenance operations required by the lighthouse's isolated location. This planning approach influenced material selection and construction techniques toward maximum longevity rather than ease of modification or repair. The maintenance planning assumptions reflected confidence in the structural design while creating long-term operational constraints that would become problematic if design assumptions proved inadequate. The emphasis on structural permanence meant that any required modifications would be exceptionally difficult and expensive to implement. The operational planning essentially committed Trinity House to the structural design choices made during the initial construction period. The integration of Bishop Rock into the broader lighthouse system around the British coastline required coordination with existing navigation aids and maritime traffic patterns. The lighthouse needed to provide distinctive light characteristics that distinguished it from neighboring lighthouses while ensuring adequate coverage of the critical navigation hazards around the Scilly Isles. This operational integration influenced the lighthouse height and light specifications while creating additional pressure. for construction completion within scheduled timeframes. The broader institutional context within which Bishop Rock was designed and constructed reflected Victorian confidence in engineering capability and systematic technological progress. The period witnessed remarkable achievements in railway engineering, bridge construction, industrial machinery, and marine engineering that demonstrated the power of scientific analysis combined with systematic construction methods. This institutional confidence provided the foundation for undertaking ambitious projects like Bishop Rock, while potentially obscuring the need for empirical validation of untested applications. The first major Atlantic storm to test Bishop Rock Lighthouse's structural adequacy occurred during the winter of 1860 to 1861, approximately 2 years after the lighthouse became operational. Meteorological records from the period document a severe weather system that approached the British Isles from the southwest, generating sustained winds exceeding 80 kilometers per hour and wave heights estimated at 12 to 15 meters. The storm system maintained these extreme conditions for approximately 18 hours as it passed over the western approaches, subjecting Bishop Rock to the most severe environmental loading it had experienced since construction completion. Trinity House maintenance records from the period provide the first documented evidence of structural response that differed significantly from design expectations. The lighthouse keeper's log entries during and immediately following the storm describe vibration of the structure that was clearly perceptible to personnel within the lighthouse. Previous storms had generated some structural movement, but the December 1860 event marked the first time that lighthouse personnel reported motion severe enough to interfere with normal operational activities. The keeper noted difficulty in maintaining lamp operation due to structural movement and expressed concern about the intensity of the structural response. Initial post-storm inspection revealed the first clear physical evidence that actual environmental forces exceeded design calculations. Trinity House engineers documented hairline fractures in several granite blocks in the middle sections of the lighthouse tower, approximately 15 to 20 meters above the foundation level. These fractures appeared in areas where structural calculations indicated stress levels should have remained well within safe limits for granite construction. The location and pattern of the fractures suggested that dynamic loading conditions were creating stress concentrations that static analysis had not predicted. More significantly, the inspection revealed slight but measurable displacement of individual granite blocks within their dovetailed joints. The displacement was minimal, typically less than 5 millimeters, but represented clear evidence that the mechanical interlocking system was experiencing forces that approached or exceeded its design capacity. The dovetailing had been designed to prevent displacement under any conceivable loading condition, yet measurable movement had occurred during the first major storm to test the structure. The observation of structural displacement during storm conditions marked a critical divergence between engineering expectations and physical reality. The design calculations had been based on wave force estimates that assumed maximum loading could be predicted from wave height using static pressure principles. These calculations indicated that a 15-meter wave would generate approximately 150 kilonewtons per square meter of applied pressure. Even with conservative safety factors, this pressure level should have remained well within the capacity of the masonry and anchoring systems. However, the observed structural response indicated that actual forces significantly exceeded these calculations. The dynamic nature of breaking wave impact created loading conditions that differed fundamentally from the static pressure assumptions underlying the original design. When waves break against a vertical structure in deep water, the kinetic energy of thousands of tons of moving water converts instantaneously to impact force. This momentum transfer can generate forces many times greater than static pressure calculations would predict. The breaking wave phenomenon that Bishop Rock experienced during severe storms involved complex fluid dynamics that were not well understood by 19th-century engineering. As storm waves approach a structure in deep water, they maintain their full energy until the moment of impact. The wave face strikes the lighthouse with tremendous velocity, creating an initial shock load as the water momentum transfers to the structure. This initial impact is followed by a complex pattern of pressure variations as water rushes up the structure face, falls back, and interacts with subsequent wave impacts. The cyclical nature of wave impact during extended storms introduced additional loading considerations that static analysis could not address. Each wave impact created stress cycles within the masonry structure, with rapid loading followed by pressure release, and then renewed loading from the next wave. During an 18-hour storm, the Lighthouse experienced thousands of these loading cycles, each approaching or exceeding the design limits of the structural system. This repetitive loading introduced fatigue effects that gradually reduced the structural integrity of the masonry and anchoring systems. Trinity House engineers recognized that the observed structural response indicated fundamental problems with the original design assumptions. The evidence was clear and undeniable. The Lighthouse was experiencing forces that exceeded design calculations by significant margins. The engineering team faced a critical decision point regarding the appropriate response to this discovery. They could attempt to modify the existing structure to increase its capacity, or they could accept the structural limitations and monitor the Lighthouse for progressive deterioration. The institutional response to the structural evidence reflected the technical and economic realities facing Trinity House. Complete reconstruction of the Lighthouse would require enormous expense and would eliminate navigation guidance for an extended period during construction. Temporary lighting alternatives for Bishop Rock were extremely limited due to the site's isolation and exposure. Any extended interruption of lighthouse operation would create unacceptable risks for maritime traffic using the western approaches. The engineering analysis of the structural evidence led to a systematic reassessment of wave force calculations and structural requirements for extreme offshore exposure. Trinity House engineers began developing new analytical approaches that attempted to account for dynamic loading effects and momentum transfer during wave impact. These revised calculations suggested that actual wave forces could exceed static pressure estimates by factors of 3 to 5, depending on wave characteristics and braking conditions. The reassessment process revealed the limited empirical foundation underlying lighthouse engineering for extreme offshore applications. While Trinity House possessed extensive experience with coastal lighthouse construction, Bishop Rock represented exposure conditions that exceeded the organization's empirical knowledge base. The engineering profession possessed sophisticated analytical tools for many applications, but wave loading under extreme offshore conditions remained largely theoretical rather than empirically validated. Concurrent developments in other engineering fields were beginning to reveal similar limitations in the application of established analytical methods to unprecedented conditions. Railway engineering was discovering that bridge loading under high-speed trains created dynamic effects that static analysis could not predict. Industrial machinery design was encountering vibration and fatigue phenomena that required new analytical approaches. The Bishop Rock experience represented part of a broader recognition within the engineering profession that dynamic loading conditions required fundamentally different analytical methods than static applications. The measurement and documentation challenges associated with extreme environmental loading became apparent during the post-storm assessment process. The isolated location of Bishop Rock made detailed environmental monitoring extremely difficult. Weather data from the storm came primarily from coastal stations that could not accurately represent conditions at the lighthouse location. Wave height estimates were based on visual observations from ships and coastal locations rather than direct measurement at the structure. The lack of quantitative environmental data created uncertainty about the relationship between storm conditions and structural response. Trinity House engineers could document the structural evidence clearly, but they could not precisely correlate that evidence with specific environmental loading conditions. This data limitation made it difficult to develop improved design standards that could be applied to future lighthouse projects with confidence. The structural monitoring capabilities available in the 1860s were limited to visual inspection and basic dimensional measurements. The engineering team could document crack patterns, measure displacement, and assess material condition through careful examination. However, they could not measure dynamic loads, stress distributions, or structural response during actual storm conditions. The monitoring approach was necessarily reactive, documenting structural changes after they occurred rather than observing the loading conditions that caused them. the implications of the structural evidence extended beyond the immediate concerns about Bishop Rock's integrity to broader questions about lighthouse engineering methodology. The experience demonstrated that extrapolation from coastal lighthouse experience to extreme offshore conditions involved uncertainties that existing analytical methods could not address. The engineering profession needed new approaches for validating structural adequacy under unprecedented environmental conditions. The operational continuity requirements for navigation safety created additional constraints on the response options available to Trinity House. Bishop Rock provided critical navigation guidance for maritime traffic approaching the English Channel from Atlantic routes. Any interruption of lighthouse operation would create immediate safety risks for vessels transiting the western approaches. The navigation continuity requirements meant that any structural modifications would need to be accomplished while maintaining lighthouse operation, significantly complicating potential engineering solutions. The documentation of structural response during the 1860-1861 storm established a baseline for ongoing monitoring of lighthouse performance under extreme conditions. Trinity House implemented systematic inspection procedures that tracked crack propagation, displacement patterns, and material degradation over time. This monitoring program provided essential data for understanding how the structural problems were evolving and for planning appropriate intervention strategies. The broader maritime community's awareness of structural issues at Bishop Rock created pressure for rapid resolution while highlighting the broader implications for offshore lighthouse design. Ship captains and maritime authorities expressed concern about the reliability of navigation aids under extreme weather conditions. The lighthouse's structural problems became a matter of public interest, creating additional pressure on Trinity House to develop effective solutions quickly. The winter storm of 1860 to 1861 thus marked a fundamental transition in understanding of offshore lighthouse engineering requirements. The event demonstrated conclusively that traditional design methods were inadequate for extreme offshore applications while revealing the complex technical, economic, and operational challenges associated with addressing structural deficiencies in critical navigation infrastructure. The structural evidence from this storm would drive the engineering analysis and modification strategies that Trinity House would pursue over the following decades. The progression of structural deterioration at Bishop Rock following the initial 1860-1861 storm revealed the complex physics underlying dynamic wave loading and the inadequacy of traditional masonry construction for extreme marine environments. Trinity House engineers initiated systematic documentation of structural changes, tracking crack propagation, joint displacement, and material degradation through successive storm seasons. This monitoring program provided unprecedented, empirical data about structural response to repeated extreme loading cycles. The granite fracture patterns that emerged over the following years demonstrated stress concentration phenomena that traditional lighthouse engineering had not anticipated. Initial hairline cracks, barely visible during post-storm inspections, propagated systematically through successive weather cycles. The crack propagation followed predictable paths determined by the granite's crystalline structure and the distribution of embedded stress concentrations. Most significantly, the cracks appeared to initiate at locations where rapid stress transitions occurred during dynamic loading cycles rather than at points of maximum calculated static stress. Detailed examination of the failed granite blocks revealed fracture mechanics that differed fundamentally from static loading failures. The fractures exhibited characteristics of rapid stress loading and release cycles rather than gradual stress accumulation. Microscopic analysis of fracture surfaces showed evidence of fatigue crack growth, with striations indicating repeated loading cycles. This evidence confirmed that the structural failure mechanism involved dynamic fatigue rather than simple overstress of the material under static loading conditions. The dovetail joint system, fundamental to the lighthouse's structural integrity, exhibited systematic degradation under the cyclic loading conditions created by storm wave impact. The original joint design had assumed that mechanical interlocking would prevent displacement under any loading condition that did not exceed the material strength of the granite blocks themselves. However, the dynamic loading created high-frequency stress cycles that gradually loosened the mechanical connections between adjacent blocks. The physics of joint failure under cyclic loading involved complex interactions between material properties, joint geometry, and loading characteristics. Each wave impact created rapid stress loading in the dovetailed connections, followed by equally rapid stress release as the wave pressure subsided. The repetitive nature of these loading cycles caused gradual enlargement of the dovetail interfaces as granite surfaces wore against each other under high-stress conditions. Over time, this wear accumulated sufficient clearance to allow measurable displacement between blocks. The metal anchoring system, designed to provide additional security for the masonry structure, experienced degradation mechanisms that further compromise structural integrity. The galvanized puddled steel bolts, while resistant to corrosion, were subjected to stress cycles that exceeded their fatigue design limits. The bolts experienced tensile loading during wave impact, followed by compression during wave withdrawal, creating alternating stress conditions throughout each storm event. Extended storms subjected individual bolts to thousands of stress cycles, gradually reducing their structural capacity. The Muntz metal bolts anchoring the foundation courses to the granite outcrop exhibited different but equally problematic behavior under extreme loading conditions. While the bolts themselves maintained structural integrity, the Fox wedging system that secured them in the rock experienced gradual loosening under the dynamic loading conditions. The repeated stress cycling caused the wedge systems to work loose incrementally, reducing the anchoring effectiveness and allowing foundation movement that had not been anticipated in the original design. The interaction between different failure mechanisms created compound structural problems that accelerated deterioration beyond what any single mechanism would have produced. Joint loosening allowed increased movement between granite blocks, which increased stress concentrations in the metal anchoring systems. Anchor degradation allowed additional structural movement, which increased stress concentrations in the dovetailed joints. The result was a cascading failure process in which each degraded system component increased the loading on other components. Wave loading physics during severe storms created force magnification effects that static calculations could not predict. When breaking waves struck the lighthouse, the initial impact created shock loads that propagated through the structure as compression waves traveling at several thousand meters per second. These compression waves reflected from structural boundaries and interfaces, creating complex stress patterns within the masonry. The interference between incident and reflected stress waves produced stress concentrations at specific locations that could exceed the incident wave force by substantial factors. The vertical distribution of wave loading on the lighthouse structure differed significantly from the uniform pressure distribution assumed in the original design calculations. Breaking waves created maximum loading in the lowest sections of the tower, where wave energy had not yet dissipated through impact and upward flow. However, the dynamic effects of wave impact and reflection created secondary loading peaks at intermediate elevations where reflected waves interfered constructively with incident wave energy. The temporal characteristics of wave loading during extended storms introduced loading frequencies that approached the natural frequency characteristics of the masonry structure. When wave impact frequency approached structural resonance conditions, the lighthouse experienced amplified response that magnified the stress levels throughout the structure. This resonance amplification could increase structural stresses by factors of 2 to 3 beyond the levels that would occur under non-resonant loading conditions. Trinity House engineers attempted to quantify the actual wave forces through indirect measurement of structural response during storm conditions. They installed simple displacement measurement devices that could record structural movement during storm events without requiring personnel presence at the lighthouse. These measurements confirmed that structural displacement increased non-linearly with storm intensity, suggesting that wave force increased much more rapidly than static pressure calculations would predict. The measurement data revealed that structural displacement during severe storms could exceed 10 millimeters at the midpoint of the tower, indicating deflections that approach the limits of masonry construction tolerances. More critically, the displacement measurements showed that structural movement continued for extended periods after individual wave impacts, indicating that the structure was experiencing sustained vibration rather than simple static deflection. This vibration response confirmed that dynamic effects dominated the structural behavior under storm conditions. The relationship between wave height and structural response provided empirical validation of the inadequacy of static pressure calculations for extreme loading conditions. Trinity House engineers documented that doubling wave height from 10 to 20 meters increased structural displacement by factors of 8 to 10, rather than the factor of 4 that static calculations would predict. This nonlinear relationship demonstrated that wave loading involved momentum transfer and dynamic amplification effects that traditional analysis methods could not capture. Material degradation accelerated significantly as structural movement increased beyond design tolerances. Granite blocks that had maintained perfect interfaces for the first several years after construction began exhibiting accelerated wear once dynamic loading created sustained movement between adjacent surfaces. The combination of high contact stresses and repetitive motion created abrasive wear that progressively enlarged joint clearances and reduced structural stiffness. The cement and mortar systems used to seal joints between granite blocks experienced catastrophic failure under the dynamic loading conditions. The original design had specified Medina Roman cement below high water levels and Portland cement above, with both systems designed to provide weather sealing while accommodating slight thermal movement. However, the dynamic loading created movement amplitudes that exceeded the design capacity of the cement systems, causing progressive joint failure throughout the structure. Inspection evidence from the mid-1860s documented the accelerating pace of structural deterioration as the cascading failure mechanisms gained momentum. Granite pieces weighing up to 25 kilograms had split completely away from the exterior face during violent storms. Joint displacement had increased to the point where weather penetration was creating interior damage to metal components and structural connections. The lighthouse remained operational, but the structural evidence indicated that the rate of deterioration was accelerating toward potential structural failure. The physics analysis of the failure progression revealed that the lighthouse had entered a regime of progressive structural degradation in which each storm cycle caused more damage than the previous cycle. The reduced structural stiffness resulting from accumulated damage meant that subsequent storms created larger displacement and higher stress concentrations, accelerating the rate of additional damage. This positive feedback mechanism indicated that structural failure would continue to accelerate unless fundamental modifications were implemented. Trinity House engineers recognized that the empirical evidence demonstrated conclusively that the original design approach was fundamentally inadequate for the environmental conditions at Bishop Rock. The lighthouse had been designed using the best engineering methods available at the time, constructed with the highest quality materials and craftsmanship, and operated according to established lighthouse management practices. Yet the structure was experiencing progressive failure under the environmental conditions it had been specifically designed to resist. The technical analysis of the failure mechanisms provided essential information for developing potential solutions to the structural problems. The engineers understood that any effective solution would need to address the dynamic loading characteristics of wave impact rather than simply increasing the capacity of the existing structural system. The failure analysis indicated that fundamental changes to either the structural design or the loading environment would be required to achieve long-term structural adequacy. The recognition that Bishop Rock Lighthouse faced progressive structural deterioration that threatened its continued operation forced Trinity House to develop comprehensive remediation strategies while maintaining the lighthouse's critical navigation function. The engineering challenge was unprecedented: how to substantially modify a structure located 16 miles from land, accessible only during brief weather windows, while ensuring continuous operation of essential navigation equipment. The solution development process would reveal additional complexities and limitations inherent in attempting to retrofit structures designed under fundamentally flawed assumptions. Trinity House commissioned detailed structural analysis to determine the minimum modifications required to ensure long-term structural adequacy. The engineering assessment needed to address both the immediate structural problems and the underlying design inadequacies that had created those problems. The analysis team included the organization's most experienced lighthouse engineers, supplemented by consulting experts in masonry construction and marine engineering who could provide independent perspective on the technical challenges. The structural assessment confirmed that simple repairs to the existing structure would be inadequate to address the fundamental design limitations. The dynamic wave loading that was causing progressive deterioration could not be reduced through minor structural modifications. The loading environment could only be modified through fundamental changes to the lighthouse profile or through substantial increases in structural mass and stiffness that would require major reconstruction. The engineering team evaluated multiple potential approaches to addressing the structural problems. Complete reconstruction would provide the opportunity to implement improved design methods but would require extended interruption of navigation services and enormous expense. Structural reinforcement through external addition could potentially be accomplished without major service interruption, but would need to address the interface challenges between new construction and the existing deteriorated structure. The selected approach involved construction of an external granite casing around the existing lighthouse structure, extending from the foundation to approximately the level of the original service room. This reinforcement strategy would substantially increase the structural mass and stiffness of the lighthouse while providing new anchoring systems that could better resist the dynamic wave loading. The design retained the upper portion of the original lighthouse, including the lantern and light apparatus, while fundamentally rebuilding the structural foundation. The external casing design incorporated lessons learned from the structural failure analysis, while attempting to minimize the technical risks associated with major construction in such an exposed location. The new construction would use larger granite blocks, improved anchoring systems, and construction techniques specifically designed to resist dynamic loading. The reinforcement would create a cylindrical base approximately 12.5 meters in diameter, rising to 12.2 meters above the foundation level, providing a stable platform for the reconstructed upper lighthouse structure. However, the reinforcement approach created complex technical challenges that had not been fully anticipated during the design development process. The interface between the new external construction and the existing deteriorated structure required careful engineering to ensure that loads would transfer properly between the two structural systems. The existing structure could not be demolished before the new construction was completed, yet the deteriorated condition of the existing structure made it an unreliable foundation for supporting construction operations. The construction sequencing for the reinforcement project required innovative approaches to manage the technical and logistical challenges of major construction in an extreme marine environment. All materials and equipment had to be transported to the site by ship and lifted to the construction level, using temporary hoisting equipment. The construction work could proceed only during favorable weather conditions, which remained as limiting during the 1880s, as they had been during the original construction 30 years earlier. The granite selection and preparation for the reinforcement construction incorporated specifications designed to address the material degradation mechanisms that had been observed in the original structure. The new blocks were quarried from stone formations that exhibited superior resistance to dynamic loading and marine environment exposure. The cutting and shaping operations included more precise tolerances and improved surface preparation to ensure better load distribution and reduced stress concentrations at block interfaces. The anchoring system designed for the reinforcement construction represented a fundamental advancement over the methods used in the original lighthouse. The new approach used longer and larger diameter bolts with improved materials and installation techniques. The anchoring pattern was designed to distribute loads more effectively while providing redundancy that would prevent progressive failure if individual anchors experienced degradation over time. The Fox wedging technique was replaced with threaded anchor systems that could be tensioned to specific load levels and inspected for degradation during routine maintenance operations. The construction quality control procedures for the reinforcement project incorporated systematic testing and validation methods that had not been available during the original construction. Load testing of anchor installations verified that individual connections met design requirements before proceeding with subsequent construction phases. Joint assembly procedures included verification of fit and alignment before final positioning and securing of granite blocks. These quality control improvements were designed to prevent the construction deficiencies that might have contributed to the original structural problems. Nevertheless, the reinforcement construction encountered technical difficulties that illustrated the fundamental challenges of major construction operations in extreme marine environments. Weather delays extended the construction schedule significantly beyond original estimates, increasing costs and creating additional risks for construction personnel and equipment. Several construction accidents occurred when equipment or materials were lost due to unexpected weather deterioration during construction operations. More significantly, the construction process revealed additional evidence of deterioration in the original lighthouse structure that had not been apparent during external inspections. When sections of the original structure were exposed during reinforcement construction, engineers discovered that internal structural elements had experienced degradation that was more extensive than external evidence had suggested. The discovery of additional structural problems required design modifications to the reinforcement system while construction was already underway. The integration challenges between the new reinforcement structure and the existing lighthouse created engineering problems that required innovative solutions developed under significant time pressure. The deteriorated condition of the existing structure meant that it could not reliably support the construction loads imposed by the reinforcement work. Temporary structural support systems were required to maintain the stability of the existing structure during reinforcement construction, adding complexity and cost to the project. The structural interface design between the old and new construction required careful analysis to ensure that loads would transfer properly between the two systems under extreme loading conditions. The reinforcement structure needed to carry the majority of the dynamic wave loading while ensuring that the existing structure would not experience stress concentrations that could cause additional deterioration. The interface design represented a compromise between optimal structural performance and the practical constraints imposed by the existing deteriorated structure. The lighthouse operation continuity during construction created additional technical challenges that affected both construction efficiency and structural design options. The lighthouse needed to maintain navigation services throughout the construction period, requiring that the light apparatus and support systems remain functional despite major construction activities immediately below. Construction operations had to be planned and executed to minimize interference with lighthouse operation while ensuring safety of both construction personnel and lighthouse equipment. The construction monitoring during the reinforcement project provided valuable empirical data about structural response under dynamic loading conditions. Measurement equipment installed during construction could record structural movements and stress levels during storm events, providing the first direct measurements of the forces that the lighthouse experienced under extreme conditions. These measurements confirmed that actual wave forces exceeded the original design calculations by substantial margins while validating that the reinforcement design would provide adequate structural capacity. The economic cost of the reinforcement construction substantially exceeded original estimates due to the technical challenges and construction delays encountered during the project. The total cost of the improved granite lighthouse reached £64,889 compared to the original lighthouse of £43,869 30 years earlier. The cost escalation reflected both the technical complexity of the reinforcement work and the logistical challenges of major construction in such an exposed location. The completion of the reinforcement construction in 1887 created a lighthouse structure that incorporated both the lessons learned from the original structural failure and the improved engineering methods that had been developed over the intervening decades. The reinforced structure provided substantially increased resistance to dynamic wave loading while maintaining the navigation function that made Bishop Rock essential to maritime safety in the western approaches. However, the reinforcement approach also created long-term maintenance challenges that would become apparent over subsequent decades. The complex interface between old and new construction created potential failure modes that were difficult to inspect and maintain. The increased structural complexity meant that future maintenance operations would require more specialized technical expertise and more extensive equipment than the original lighthouse had required. The reinforcement project established important precedents for addressing structural inadequacies in critical infrastructure under extreme environmental conditions. The experience demonstrated that fundamental design limitations could be addressed through major reconstruction, but at substantial cost and with significant technical risks. The project also illustrated the importance of maintaining operational continuity during infrastructure modification, even when that continuity imposed additional technical constraints on the modification approach. The long-term performance monitoring of Bishop Rock Lighthouse, following completion of the reinforcement construction in 1887, provided unprecedented empirical data about the effectiveness of engineering solutions for extreme marine loading conditions. Trinity House implemented systematic inspection and monitoring procedures that tracked structural performance through successive storm seasons, documenting both the success of the reinforcement approach and the persistent challenges associated with maintaining critical infrastructure under extreme environmental conditions. Post-reinforcement structural performance data confirmed that the external granite casing had successfully addressed the most critical aspects of the original design inadequacy. Structural displacement measurements during severe storms showed substantial reduction compared to the pre-reinforcement period. Where the original structure had experienced displacement exceeding 10 millimeters during major storms, the reinforced structure typically exhibited displacement of less than 2 millimeters under similar conditions. This improvement demonstrated that the increased structural mass and improved anchoring systems were effectively resisting the dynamic wave loading that had caused progressive deterioration of the original structure. The inspection evidence also validated the engineering analysis that had identified dynamic loading as the fundamental cause of the original structural problems. The original lighthouse structure, now protected within the reinforcement casing, showed no significant additional deterioration following completion of the reinforcement construction. The cessation of progressive damage in the original structure confirmed that external loading, rather than inherent material deficiencies, had been responsible for the structural problems observed during the 1860s and 1870s. However, the monitoring program also revealed that the reinforcement approach had not eliminated all sources of structural stress under extreme loading conditions. The interface between the original structure and the reinforcement casing experienced ongoing movement under severe storm conditions. While this movement was much smaller than the displacement experienced by the original structure alone, it indicated that the complex structural system created by the reinforcement approach had its own limitations under extreme loading. The wave force measurements obtained during the monitoring period provided the first quantitative validation of the inadequacy of the original design calculations. Direct measurement of wave impact forces during severe storms confirmed that actual forces exceeded static pressure calculations by factors ranging from 3 to 8, depending on storm characteristics and wave-breaking conditions. These measurements provided empirical validation of the engineering analysis that had concluded that dynamic momentum transfer effects dominated the loading environment at Bishop Rock. The measurement data also revealed the complex temporal characteristics of wave loading during extended storms. Rather than experiencing sustained pressure as static calculations had assumed, the Lighthouse experienced thousands of individual impact events during major storms, each lasting only seconds but creating forces that peaked well above average loading conditions. The cumulative effect of these impact cycles created fatigue loading conditions that traditional lighthouse engineering had not anticipated. Comparative analysis of structural performance before and after reinforcement provided clear evidence of the relationship between structural characteristics and resistance to dynamic loading. The reinforcement had increased the structural mass of the lighthouse by approximately 400% while improving the stiffness of the foundation connection by similar amounts. The combination of increased mass and stiffness had reduced structural displacement under extreme loading by factors of 5 to 6, confirming that these structural characteristics were critical for resistance to dynamic wave loading. The monitoring program documented that the reinforced lighthouse structure met all performance requirements for navigation safety while demonstrating adequate structural durability under extreme environmental conditions. The lighthouse maintained reliable operation throughout the most severe storms of the late 19th and early 20th centuries without experiencing structural problems comparable to those that had threatened the original structure. The reinforcement approach had successfully transformed Bishop Rock from a structure of questionable long-term viability to a lighthouse that could provide reliable navigation services indefinitely. The economic analysis of the reinforcement project revealed that the total cost of addressing the structural inadequacy substantially exceeded the cost of the original lighthouse construction, including the original construction cost of £43,869 and the reinforcement cost of £64,889. The total investment in Bishop Rock Lighthouse reached £108,758 by 1887. This compared to typical lighthouse construction costs of £25,000 to £50,000 for less exposed locations during the same period. The cost comparison illustrated the economic consequences of inadequate initial design for extreme environmental conditions. The institutional learning implications of the Bishop Rock experience influenced lighthouse engineering methodology throughout the British lighthouse system and internationally. Trinity House incorporated wave force measurement and dynamic loading analysis into design procedures for subsequent lighthouse projects. The organization developed improved methods for estimating wave forces under extreme conditions while implementing more conservative safety factors for offshore lighthouse design. The technical knowledge gained from Bishop Rock influenced the broader engineering profession's understanding of dynamic loading and structural response under extreme environmental conditions. The experience contributed to the development of improved analytical methods for predicting structural response to dynamic loading, while highlighting the importance of empirical validation for engineering applications beyond the range of previous experience. International lighthouse authorities studied the Bishop Rock experience as they planned their own lighthouse construction projects in exposed marine environments. The technical documentation of the structural problems and the reinforcement solution provided valuable guidance for lighthouse engineering in locations with similar environmental challenges. The experience influenced lighthouse design standards in numerous countries while contributing to the development of international best practices for marine structure engineering. The regulatory implications of the Bishop Rock experience led to enhanced oversight of lighthouse construction and more systematic requirements for structural adequacy validation. Maritime safety authorities recognized that lighthouse structural failure could create navigation hazards that affected international shipping, justifying more rigorous engineering standards and independent review of lighthouse design for critical locations. The broader engineering significance of the Bishop Rock experience extended beyond lighthouse applications to fundamental questions about engineering methodology for unprecedented applications. The experience illustrated how institutional confidence in proven engineering methods could obscure the need for empirical validation when those methods were applied beyond their validated range of conditions. The case demonstrated the importance of distinguishing between engineering applications where extrapolation from existing experience was adequate and applications where new empirical data was required. The structural monitoring data from Bishop Rock contributed to the development of improved understanding of wave loading physics and structural response mechanisms that would benefit marine engineering applications throughout the 20th century. The empirical data about dynamic loading characteristics provided validation for theoretical models while identifying phenomena that required new analytical approaches. This knowledge foundation supported the development of offshore oil platforms, coastal protection structures, and marine installations that would face similar extreme loading conditions. The long-term maintenance experience with the reinforced lighthouse revealed both the benefits and limitations of the reinforcement approach for addressing fundamental design inadequacies. While the reinforcement successfully prevented further structural deterioration and ensured reliable lighthouse operation, it also created a complex structural system that required specialized maintenance expertise and techniques. The maintenance requirements were manageable but substantially exceeded those of simpler lighthouse structures in less exposed locations. The personnel safety implications of the Bishop Rock experience influenced Trinity House policies for lighthouse construction and maintenance in extreme environments. The organization developed enhanced safety procedures for construction work in exposed marine locations while implementing improved training programs for personnel working on extreme environment projects. These safety improvements reduced the risks associated with lighthouse operations while ensuring that critical navigation services could be maintained even under challenging conditions. The historical significance of Bishop Rock Lighthouse as a case study in engineering failure and remediation established its importance as a learning resource for the engineering profession. Technical education programs incorporated the Bishop Rock experience into curricula covering structural engineering, marine engineering, and engineering project management. The case provided a clear example of how engineering assumptions could fail under unprecedented conditions, while illustrating both effective and problematic approaches to addressing engineering challenges. The continued operation of Bishop Rock Lighthouse throughout the 20th and into the 21st century validated the effectiveness of the reinforcement approach, while demonstrating the long-term value of addressing infrastructure problems through comprehensive engineering solutions. The lighthouse continues to provide navigation services more than 130 years after completion of the reinforcement construction, confirming that the engineering analysis and remediation were successful in achieving their fundamental objectives. The legacy of the Bishop Rock experience remains relevant to contemporary engineering challenges involving infrastructure design for extreme environmental conditions. Climate change, more frequent extreme weather events, and the need for infrastructure in increasingly challenging locations create contemporary parallels to the engineering challenges that Trinity House faced in the 19th century. The lessons learned from Bishop Rock about the importance of empirical validation, conservative design approaches, and comprehensive problem analysis continue to inform engineering practice for critical infrastructure applications. The technical documentation and analysis of the Bishop Rock case established important precedents for engineering failure investigation and remediation that influenced professional standards for engineering project management and quality assurance. The systematic approach to problem analysis, solution development, and performance validation demonstrated effective methods for addressing complex engineering challenges while maintaining operational requirements for critical infrastructure.